You're sitting at your desk, pencil in hand, staring at a physics problem that looks deceptively simple. Maybe it's a question about a ball rolling down a ramp or a circuit with a couple of resistors or a projectile launched at an angle. You think, I've got this. You scribble down your answer, feeling confident, until you check the solution and realize you're way off. Your heart sinks. Where did you go wrong? If this sounds familiar, you're not alone. In fact, you've just joined the ranks of every physics student ever. The truth is, physics isn't just about memorizing formulas or plugging numbers into equations. It's about understanding the hidden rules that govern the universe and the sneaky traps that can trip you up when you least expect it. Today we're going to shine a light on the most common physics mistakes, the ones that even the smartest students make. These aren't just little slip-ups. They're the kinds of errors that can cost you points on an exam, or worse, make you doubt your own abilities. But here's the good news. Once you know what to watch out for, you can avoid these pitfalls and start thinking like a true physicist. So grab your notebook, because by the end of this video, you'll be armed with the knowledge to dodge the most dangerous traps in physics. Let's start with a classic, confusing mass and weight. It sounds basic, right? But you'd be amazed how often this mistake shows up, even in advanced classes. Mass is the amount of matter in an object measured in kilograms. Weight is the force of gravity acting on that mass measured in newtons. On Earth, your weight is your mass times the acceleration due to gravity, about 9.8 meters per second squared. But take that same mass to the moon, and your weight drops to about 1/6, even though your mass stays the same. Mix these up, and you'll get the wrong answer every time. Remember, mass is what you have. Weight is what you feel. Now let's talk about signs. No, not the kind you see on the road, the plus and minus signs in your equations. This is one of the sneakiest mistakes in all of physics. You're working on a problem, you set up your equation, and somewhere along the way, you drop a negative sign. Suddenly, your answer is off by a factor of 2, or you get a result that makes no physical sense, like a negative distance or a force pointing the wrong way. The key is to be consistent. Define your coordinate system at the start of the problem and stick to it. If up is positive, then down is negative. If right is positive, then left is negative. Don't let a missing sign derail your solution. Here's another big one. Forgetting about units. You've probably heard the story of the Mars Climate Orbiter, a $125 million spacecraft that crashed because engineers mixed up metric and imperial units. One team used newtons, the other used pounds. The result? Disaster. In physics, units are your best friend. They tell you if your answer makes sense, and they can even help you catch mistakes before they happen. Always write your units, and always check that they match on both sides of the equation. If you end up with meters per second squared when you're supposed to have meters, you know something's gone wrong. Let's move on to vectors. Physics is full of quantities that have both magnitude and direction, velocity, force, acceleration. But it's all too easy to treat them like simple numbers. You add them up without thinking about their direction, and suddenly your answer is way off. Remember, vectors aren't just numbers, they're arrows, and you have to add them head to tail, not just by adding their magnitudes. If you're working in 2 or 3 dimensions, break each vector into its components, add the components separately, and then recombine them at the end. It takes a little extra work, but it's the only way to get the right answer. Now let's talk about friction. It's one of those forces that everyone thinks they understand until they don't. The most common mistake? Assuming friction always acts to oppose motion. In reality, friction opposes relative motion between surfaces. That means if you're walking forward, the friction from the ground actually pushes you forward, not backward. It's what lets you walk, drive, or even hold a pencil. Another common error is forgetting that static friction can be greater than kinetic friction. Just because an object isn't moving doesn't mean there's no friction. It just means the frictional force is balancing out other forces. Don't let friction trip you up. Let's not forget about energy. One of the most common mistakes is assuming that energy is always conserved no matter what. But in real life, energy can be transformed into forms you might not be tracking, like heat, sound, or light. If you're solving a problem and you can't account for where all the energy went, you're probably missing something. Always ask, is this a closed system? Are there any non-conservative forces like friction or air resistance at work? If so, you need to include them in your calculations. Now let's talk about free body diagrams. These are the bread and butter of physics problem solving, but they're also a common source of mistakes. The biggest error? Leaving out forces or including forces that don't exist. Every force should have a clear source and a clear direction. Gravity always points down. Normal force is always perpendicular to the surface. Friction is parallel to the surface and opposes relative motion. Tension pulls along the direction of the rope or string. If you're not sure whether to include a force, ask yourself, what's causing it? If you can't name a source, it probably doesn't belong. Here's a subtle one, confusing speed and velocity. Speed is a scalar. It has only magnitude. Velocity is a vector. It has both magnitude and direction. If you're running around a track and end up where you started, your average speed might be high, but your average velocity is 0. This distinction matters, especially when you're dealing with problems involving displacement, acceleration, or momentum. Always pay attention to direction. And finally, let's talk about assumptions. Every physics problem comes with a set of assumptions, some stated, some hidden. Maybe you're told to ignore air resistance or to assume a surface is frictionless. Maybe you're told an object is a point mass or that a spring is ideal. These assumptions simplify the math, but they can also lead you astray if you forget about them. Always read the problem carefully and make a list of the assumptions you're making. If your answer doesn't make sense, go back and check your assumptions. Let's dig deeper into the world of physics mistakes, because the truth is, even the most experienced physicists can fall into these traps. The difference is they know how to catch themselves, and you can too. Let's look at some real-life scenarios and classic blunders that have tripped up students and professionals alike and see how you can avoid them. Imagine you're working on a projectile motion problem. You're told a ball is launched at a certain angle with a certain speed, and you're asked how far it will travel before hitting the ground. It seems straightforward, but here's where many students slip. They forget to break the motion into horizontal and vertical components. The ball's velocity isn't just in one direction, it's split between up and forward. If you try to use the total speed in your equations for vertical motion, you'll get the wrong answer. The key is to use trigonometry. The horizontal component is the speed times the cosine of the angle, and the vertical component is the speed times the sine. Only by treating each direction separately can you solve the problem correctly. Now, let's talk about circular motion. You're told an object is moving in a circle at a constant speed, and you're asked about the forces involved. A common mistake is to think that if the speed is constant, there's no acceleration. But in circular motion, even if the speed doesn't change, the direction does. And that means there's always an acceleration toward the center of the circle, called centripetal acceleration. If you forget this, you'll miss the force that keeps the object moving in a circle. This is why, for example, you feel pushed outward when a car turns sharply. The car is actually pushing you inward, and your body wants to keep moving in a straight line. Let's move on to electricity and circuits. One of the most common mistakes is confusing series and parallel circuits. In a series circuit, the current is the same through every component, but the voltage is divided among them. In a parallel circuit, the voltage is the same across each branch, but the current is divided. Mix these up and your calculations will be off. Another classic error is forgetting that resistors in series add up, while resistors in parallel combine in a more complicated way. The reciprocal of the total resistance is the sum of the reciprocals of each resistor. It's easy to get tripped up if you're not careful, so always double check your circuit diagrams and your math. Thermodynamics is another area full of pitfalls. One of the biggest mistakes is confusing heat and temperature. Heat is energy transferred between objects because of a temperature difference, measured in joules. Temperature is a measure of the average kinetic energy of the particles in a substance, measured in degrees Celsius or Kelvin. You can add heat to an object without raising its temperature if the energy goes into changing the state, from solid to liquid, for example. This is why ice can melt at a constant temperature, even as it absorbs heat. Don't let the terms trip you up. Heat is energy in transit. Temperature is a measure of energy. Let's talk about waves. Many students assume that when a wave travels through a medium, the particles of the medium move along with the wave. But in most cases, the particles only oscillate around their equilibrium positions. The wave itself is a disturbance that moves through the medium. This is true for sound waves in air or ripples on a pond. If you imagine the particles moving with the wave, you'll get the wrong picture of what's really happening. Always ask, Is the wave transporting energy or matter? Now let's look at Newton's laws, especially the second law, F handpans ma. A common mistake is to forget that the net force is what matters, not just any force. If multiple forces are acting on an object, you have to add them up, taking direction into account to find the net force. Only then can you use F ma to find the acceleration. If you just plug in the value of one force, you'll get the wrong answer. This is especially important in problems with friction, tension, or multiple objects connected by ropes or pulleys. Another classic error is misunderstanding action and reaction pairs in Newton's third law. If you push on a wall, the wall pushes back on you with an equal and opposite force. But these forces act on different objects, you and the wall, not on the same object. It's easy to get confused and think they cancel each other out, but they don't. Each force acts on a different body, and both are real. Let's not forget about significant figures and rounding. In physics, the precision of your answer matters. If you're given data with two significant figures, your answer should have two significant figures. Rounding too early or too late can lead to errors, especially in multi-step problems. Always keep extra digits in your calculations and round only at the end. Now let's talk about graphs. Physics is full of graphs: position versus time, velocity versus time, force versus displacement. A common mistake is to misinterpret what the slope or area under the curve represents. For example, the slope of a position versus time graph gives you velocity, while the area under a velocity versus time graph gives you displacement. Mixing these up can lead to the wrong conclusions. Always check the axes and units before you start analyzing a graph. Finally, let's discuss the importance of checking your answers. It's easy to rush through a problem, get an answer, and move on. But a true physicist always asks, does this answer make sense? Is the number reasonable? Are the units correct? If you calculate that a car is traveling at 5,000 meters per second, you should pause and reconsider. Unless you're working with rockets, that's probably not right. Estimation and sanity checks are powerful tools for catching mistakes before they cost you points. Physics is a subject that rewards careful thinking and attention to detail. The most common mistakes aren't about not knowing the material. They're about rushing, making assumptions, or overlooking the basics. By slowing down, double-checking your work, and thinking critically, you can avoid these traps and become a more confident problem solver.